Hello everyone, my name is Francisco Rivas from Loyola University. In this presentation, I'm going to talk about thermo-optical and thermo-elastic effects on board the LISA Pathfinder mission. LISA Pathfinder was a mission that had two main objectives, namely to test the technology needed to build a gravitational wave observatory in space and to measure the forces of a non-gravitational nature between two release masses in free fall conditions, as you can see here. We could measure the relative distance between these two test masses by means of a laser system placed on an optical bench between both test masses. In this slide, we can see the residual acceleration spectrum for measured during the mission. Specifically, the best result, the red line, was obtained during February 2017. Several of the forces of a non-gravitational nature that are part of this spectrum are of a thermal nature. Specifically, we can distinguish two types of thermal disturbances, those that produce real forces on the test masses and those that produce changes in the optical path of the laser beam that measure the relative distance between the test masses. Regarding the former, thermal effects that produce real forces on the test masses, we have three main mechanisms that occur within the GRS, the gravitational reference sensor, and that generate real forces on the test masses. Radiation pressure effect, this one, radiometer effect, which is related to Brownian noise and is the dominant effect in the flat part of the residual acceleration spectrum, around 1 milliards. Okay, here is the dominant effect for this flat part, for this spectrum. And finally, asymmetric outgassing. Regarding thermal effects that produce changes in the length of the optical path, we distinguish two: thermo-optical effects, this first one, and thermo-elastic effects. First, thermo-optical effects occur when we have thermal fluctuations around the optical windows. These two components you can see in this image. These optical windows were the interfaces between the optical bench, where the laser was placed, and the test masses. Thermal fluctuations produce changes in the length of the optical path as a consequence of these two physical mechanisms: temperature-induced change of the refractive index, given by this equation, and thermomechanical induced change of the refractive index as a consequence of a stress that appears because of the different thermal coefficients of the glass and of the titanium flame that claim this glass of the window. On the other hand, we have thermo-elastic effects that occur when we have thermal disturbances in the struts, this component that are the support between the LISA technology package, okay, the main scientific instrument in LISA Pathfinder, and the LISA Curie chamber. These thermal disturbances cause elongation of these supports, which in turn cause the optical path length to change. These thermal effects introduce new terms in the equation that give us the residual acceleration between both test masses, these delta G equations. Namely, you can see these first two terms for the thermo-optical disturbances produced in the optical windows. This one for the strut disturbances, thermo-elastic effect, and this other one, the optical event, that is related to this first one, because when we produce an elongation of the strut, we produce a movement in this component, in the optical event where we have the laser. To measure these thermo-optical and thermo-elastic contributions, we performed several experiments during the missions. To estimate the thermo-optical contribution, we induce thermal signal with heaters that we had on the optical windows, this red dot. You can see here in this real image of the LISA technology package. Being able to measure the temperature produced by this thermal signal induced with the heaters, being able to measure the temperature with the thermal sensors you can see here, the blue dot. We have 3 thermal sensors on each optical windows. As a consequence of these temperature perturbations, we were able to observe a change in the measured acceleration between the 2 test masses. A signal such as you can see in this plot. In fact, in this slide, you can see the measured acceleration given by the blue line, while the red line, this other one, give us the feed produced using the model that we have at the top of this slide, these 2 models, one for each optical window. And that depends on the temperature measured with the thermal sensors on the optical windows, this element here. Similarly, we induce thermal signal with heaters on the strut. You can see here the red dot on the heaters. And these thermal signals produce a change in the optical path, which in turn produce a change in the acceleration between the masses. We can observe in this slide the acceleration given by the blue signal, this one. And the feed produced using the model that we have at the bottom of this slide, this one, and that depends on the temperature measured with a thermal sensor on the strut in which we apply the thermal signal with the heater. Then with this model, we obtain a coefficient that gives us the contribution of these thermo-elastic effects for each of these strata. Finally, we also observe during the noise runs carried out during the mission that a thermomechanical disturbance appeared, produced as a consequence, this term, as a consequence of a relative movement between the optical bench and the gravitational reference sensor. This perturbation introduced a new term in our equation for the residual acceleration between both the masses, okay, this term, inside the blue circle. In this slide, we can see how the signal measured for this term during one of the noise runs we carry out during the mission shows a great dependence on temperature. As you can see here, the temperature measured, for example, with the thermal sensors located on the optical bench where we have a laser system, and you can see how we can fit very well these contributions you have here in the previous slide, showing a good correlation with temperature. Then we can see, thanks to the feeds shown, the contribution for the February 2017 noise run of these thermo-optical, thermo-elastic, and thermomechanical effects compared to the total residual acceleration. And then we can produce this plot, for example. The solid black lines give us the thermoelastic contribution produced by thermal fluctuation on the struts. The 2 lower lines, these 2, one, the solid blue line and the solid red line, the disturbances produced by each optical window, giving us the thermo-optical contribution. And finally, this dash line gives us the contribution of this thermomechanical effect produced as a consequence of a relative movement between the optical bench and the gravitational reference sensors. You can compare then, as I said before, these contributions with the total residual acceleration between both the masses. For example, for this noise run measured during February of 2017. As you can see, the thermomechanical effect is the most dominant of all these thermo-elastic, thermo-optical, and thermomechanical effects. Then finally, as conclusions, we have carried out different thermal measurements and thermal experiments during the missions. The thermo-optical and thermoelastic contributions are low compared with the total residual differential acceleration measured during a noise run, roughly 10 to the power of minus 18 meter per second squared per hertz for the thermo-optical effects, and roughly 7 times 10 to minus 18 meters per second squared per hertz for the thermoelastic effects at more or less 550 microhertz. However, the thermomechanical distortion due to the relative movement between the optical bench and the URS is higher, reaching this value you can see here at that frequency. As we saw in the previous slide, this contribution for the low frequencies regime is quite important. That's all. Thank you very much for your attention.